So, good morning, everybody, and welcome to the second day of the ARIM 3D conference. And I hope that yesterday everything is good, was gone good. I hope you enjoyed the talk, the plenary, and the roundtable and the workshop and so on. So, first of all, I would like to thank Ellen and Filippo for giving me the opportunity to be chair of this plenary session. And let me introduce our invited speaker. So, let me introduce Alessandra Sciutti. Thank you. So a big applause to Alessandra Sciutti. So just a brief introduction. So Alessandra Sciutti is a senior researcher of the contact unit. She's also the head of the contact unit, cognitive architecture for collaborative technologies of Istituto Italiano di Tecnologia. So we are talking of excellence in the field of robotics from a national perspective, but also worldwide. She was involved in many national and international projects, ERC and so on, and her research field are mainly in the framework of the human-human interaction and also human-robot interaction. Correct me if I'm wrong. So I think that the best is yet to come. So, Alessandra, the floor is yours. Thank you.
Thank you. Thank you very much. So, good morning, everybody. It's actually a great pleasure for me to be here and give you an idea of why I'm working on those topics. So, every day we hear how well the advancement in AI and robotics are going, and it's really amazing. On the other hand, we still continue every year to see our technologies suddenly and unexpectedly fail. And this happens always when this technology is confronted with us humans. So this is really puzzling and also a bit annoying if you think, particularly annoying because this technology fails in situations that are super easy for us, really literally a child's play. Indeed, if we look at how humans develop skills, we realize that at the very beginning of our life, we are already much better than our most advanced machines. Before we learn to talk properly, before 18 months of age, we learn to instrumentally help, which means the toddler looks at a person trying to complete a goal, I don't know, putting books into a closet, realizes that the person can't do that, doesn't succeed, and jump in and helps. So this is something we learn before we learn to properly speak. And our machines that can produce beautiful text can't do even the first part, which is inferring the intention of the person. So, what I believe is actually missing to our wonderful advanced machines is what I define as cognitive compatibility with the human. And two are the elements that are mostly crucial when you want to have something that is compatible at the cognitive level with you. So, the first thing is intuition. So, one thing that makes us humans so good at interacting with each other is that we see beyond the mere reality that is in front of our eyes. We actually interpret what the other person is doing, what the other person is telling, also as a function of our inference about his or their internal state. So we see and we use also the evaluation of the affective state of the other to make sense more of what these people mean. The other element that is crucial in human cognition is the ability to predict. Our brain is really designed to live in the future because we have a lot of sensory motor delays in our body. We wouldn't be able to shake a hand or fetch a ball if we were to rely on a purely reactive behavior. So we are predictive. And this means that when I'm looking at you passing to me an object, for instance, I'm already predicting what is going to happen next, what I will do next. And we want our robots to do the same as well. A lot of this as a basic that is quite simple for us, which is embodied communication. This means that in every moment, each of my actions is also a form of communication for you. This is something that we gain already from evolution. The fact that, I don't know, if I'm looking at the glass of water, you will already infer that I will probably take that. So, or the fact that you use the prosody, the tone of my voice, to understand my state of agitation. So, these forms of embodied communication is really what constitutes the basis of our establishment of shared goals and intention. And then on the tip, of course, on top of that, we can build our ability to speak and communicate. So our work is to try and reach cognitive robots by leveraging this basic ground of embodied communication, and on top of that, creating a cognitive architecture that enables the robot also to predict and have an intuition of the partner in order to adapt to our needs. And this pass necessarily, in my view, from the necessity to understand those signals that we know represent the grounding of our mutual understanding. So, understanding, for instance, something more of what's happening just by processing the way a person moves. And we have several examples. Today, I will just give you a few. But for instance, whenever we are manipulating an object, our brain chooses a different way to do that, a different dynamics and kinematics to optimize the movement. With the evolution, though, this became also a message for the others. So if I'm manipulating a heavy object, you immediately know that just by looking at my movement. And this is something that we have modeled on our robot so that it can just monitor the movement of a person and in real time detect whether the object is fragile or not, even not being able to look properly at the object. But if we don't look just at the body, but we look at the eyes of a person, well, our robot can gain also a deeper insight, closer to the intuition I was mentioning. Because we demonstrated that by monitoring pupil dilation, for instance, the robot can understand when a person is lying, or more precisely, it can monitor a potential increase of cognitive load. During a task done in collaboration, we tested it in a game. So this tells us that with a very simple signal, dependent on the way the eyes change their diameter, we as a robot can have a sense of how cognitively loading is the scenario, the situation. And of course, as I told you, these are examples, but there is still so much more of these signals that we can use to help our machines to understand us better. And analyzing one by one allows us to see how rich, how powerful those signals are in isolation. But then, if you combine them, you can reach the ability for the machine to understand something even more complex. In one of these examples, for instance, we demonstrated that the robot could understand whether a person was comfortable or not during an interaction. And this is, of course, a very important starting base if we want our robot to understand when they fail and adjust their behavior accordingly. So, the first staple for us is enable the robot to understand, to be sensitive to embodied communication. This will allow them to predict us better. Very good, but this is just one side of the communication. Because when we are collaborating with an agent, we want it to understand us, but we want us to be able to understand it as well. And so, what we want is that our robots become intrinsically comprehensible, legible as we are. So, if they know how our brain works, so which kind of signals are communicative for us, then they should find a way to reuse similar signals, similar strategies to be automatically or easy to understand for us. And we were talking about before the possibility to express the fragility of an object just with our human movement. Well, can a robot do the same? So can we have a robot that manipulates an object and we immediately know that this object needs to be treated with care? And the answer is yes. Actually, we explored the possibility of generating synthetic velocity profile that then the robot uses, and we found out that people observing the robot moving object that way immediately understood that the object needed to be treated with care. And of course, we started working with our humanoid robot, the iCub, which is the one we use the most. But then we replicated the very same principle on less humanoid robot. We started with the Baxter, then we moved on even with less humanoid construction, like the Kinova arm. And we found out that this property generalizes. That is, the robot moving according to this velocity profile automatically express to the human partner the fragility of the object. And we found also another thing, that this has quantitative advantages in terms of collaboration. The collaboration becomes more fluid, becomes faster. So this tells us that we might need as developer to take care a bit more and put more effort in developing and designing bio-inspired movements for our robots to facilitate the collaboration with them. And of course, we want robot to express properties of the object it is manipulating, but we want it also to be transparent about itself. So we behave, for instance, very differently when we have an urgency, when there is an emergency. We become very imperative, almost aggressive in our behavior. And we are very different in day to day life. We are gentle. And our brain is very sensitive to this subtle difference and reacts differently. So we studied whether we could have this kind of subtle modulation also in robot movement. So here you see a passing, very simple action, but you don't even see the face, it's just the movement. But we replicated after several attempts the signature of it being a gentle movement versus an aggressive and imperative movement. And we are confident that we managed to really replicate these vitality forms on our robot because we verified with neuroimaging. So the area of our brain that is sensitive to the modulation of the how of an action, of the style of an action, responded to our to our humanoid movement similarly to when the person was observing a human movement. So we demonstrated that the right movement of a humanoid can tap into the very same circuits that normally are activated during human-human interaction. And why do we care? Well, these are behavioral consequences. When the robot points or passes an object with an aggressive velocity profile, then our movement next becomes aggressive. So this means that subtle modulation in the simplest of the action can immediately and implicitly change the tone of interaction. And again, we tested it extensively, and we're testing it extensively with our humanoid robot. But also, this principle generalizes because we replicated a similar style contagion, also not using the humanoid robot iCub, but a manipulandum, so absolutely non humanoid, and a physical interaction. In this case, the arm was providing a gentle or let's say an aggressive physical perturbation to the participant. And we found out that when the person was moving the handle themselves, well, they were more aggressive or more gentle accordingly. So, again, these are two examples. There are so many things that we are continuously communicating, also to facilitate mutual understanding in our daily life, and there is still so much more to be investigated. But this, as I mentioned at the beginning, is really just the ground, is the basic of action and perception that it's helpful for the robot to make a basic sense of the human being it has in front of itself. But on the other hand, each of us is different. Each of us grows and changes. And therefore, what we need is to endow our robot also with the ability to grow, to change, to learn, to adapt. And to do that, we are exploring different solutions, also different technical approaches to create a cognitive architecture that could allow the robot to do so. One of the first challenges is that of identifying a good way to develop a memory for the robot. So we created a simple task to have an excuse to meet a lot of people. So the robot teaching yoga, so showing the pose and then online evaluating and correcting the pose of the person. But the idea here is that this is an excuse to encounter people multiple times and have the robot try to create a full and growing representation of each of the person, also using LLM and trying to representing through knowledge graph what the robot knows, combining the information derived from the physical exercise that it is monitored and at the same time information coming from the exchange of chat, so that the next time maybe the robot will remember that you had an injury in your right leg and that was the reason why the crab pose was not working so fine, and maybe adapt the training accordingly. Another big problem or big challenge, in a sense, for the future of our robots is that we want them more autonomous. Autonomy means that they need to have a good reasons to take a decision among the things that we program them to be able to do. And so our research toward a cognitive compatible robot is going toward the idea of creating or defining internal drives that the robot that could guide the robot to take a decision, and beyond the classical internal drives that exist in robotics, like the need for energy or maybe the need curiosity, so the need to discover something new. We have explored the need for comfort, which is inspired loosely to the way our cortisol hormone works in humans. And we found out that by creating a cognitive architecture that uses and balances out these different internal drives, the very same architecture can give rise to very different robot personalities and very different dynamics of interaction, just as a function of the relative weight given to the different drives. And we also found in an experiment of a simple game based collaboration that comparing a robot that changes its behavior based on a comfort motivation versus a standard approach, the robot resulted much more persuasive, more prone to convince the person he was working with to change their mind and follow the suggestion of the robot. The overall and final goal would actually that of having an always on robot, that is a robot that learns over time, that we don't turn off and then turn on and activate for a new specific task, but a robot that learns over time, that discovers by itself what matters in the environment and for it given their goals. And so we are combining all I mentioned before in terms of action skill, perception skill, internal drives, memory formulation in this architecture where we are trying taking a very strong developmental inspiration, so starting from the inspiration from what a newborn or a very young child can do, while we want our robot to be able to autonomously discover regularities in the environment. So discover when there are moments of activity in the room it is, or moments of calm, and then be able to predict when they will happen next in the future. So the plan is to have iCub next week, being able to remember that I take coffee at 1 p.m. and so arrive there at the coffee machine and have the iCub already preparing it for me. The interesting aspect of this research, I showed you just a few aspects more related to basic advancement, is that they have interesting outcome that can go beyond the laboratory. Several of the principles that we've studied from basic science actually were deemed quite useful in European projects for companies in the field of manufacturing or for application in a social context, such as school or museums. To recap, this is Erzelli in Genoa, where I work. What we are doing is, well, we try and take everything that science as gives us as tools. So from neuroscience, psychology, philosophy, um, motion control, So all the approaches that we combine to try and understand what are the sensory, motor, and cognitive basis of the incredible ability that humans have to interact and help each other. And when the tools that are available are not enough, we design our own. We, for instance, designed a sensorized object to investigate more in depth um, manipulation and exploratory skills and their development. When we believe we have sufficient good model of how humans solve a certain task, what we try is to implement it onto our robotic platforms, usually the ICAB. And this gives us a precious advantage in the sense that we can put the models at test. We have a device that we can control, but at the same time can actually interact with people and environment in real interaction, in real settings. What are we doing now? Well, what we are trying to face now is to develop cognitive architectures or a cognitive architecture that should enable the robot to learn over time, to memorize, to collaborate autonomously, ideally combining this prediction and intuition that I was mentioning before and that we believe are the key component in a human-human interaction, with the idea of creating machines that are actually useful, that can give explanation, that can be actually followed by the human partner, or that can actually collaborate with humans, being mindful of the state of the partner. And one of the biggest challenge, if you want, is also that of going beyond the dyadic interaction we usually target to group interaction, which of course holds its own challenge. The overall goal, and this is a goal that I'm repeating since, I don't know, 10 years, but I think I will repeat for longer, it's to obtain more humane technologies, where humane doesn't mean that they have to look like us. That's okay, can be helpful, but not necessarily. Humane means that they are aware of how we think, of how we work, so that they can adapt to us. And this, of course, is a topic that goes beyond our own group. The theme of cognitive robotics is a wide team. I'm currently one of the co-chair of the technical committee of cognitive robotics of IEEE RAS. We need to know more about how we can be useful to maximize the expansion, if you want, of the knowledge of cognitive robotics as a multidisciplinary kind of discipline. And that's something that is relevant also beyond research. So if you want to participate, it's free. So please check the website. And this year we also won the most active technical committee, so we are active. We want to do more. Let us know how we can do that. And with that, thank you for your attention and thank to the wonderful people that actually did all the work I presented today. Hi.
So, thank you, Alessandra. Thank you for your so inspiring presentation and talk. So, I think that we can open the discussion. So, we have any question from the audience? So, don't be shy. So, I think that we can start with my question. So, just for the first one, so I was very fascinated in the section where you mentioned that through the collaboration between the human and the robot action can influence the decision of the human one, and it's quite interesting because it means that the robot behavior can influence and modify the human one. So and my question was during all the tests, the tests that you have performed with the videos and so on, did you evaluate the physiological response of the human? So, for example, some physiological signals. So, for example, when would the person decided to modify his behavior, which kind of reaction we can see from the physiological signals? So, for example, a sense of frustration or I don't know. So thank you.
Thank you. Indeed, there are different ways in which apparently the robot is able to modify the decision and also the behavior of the person. A lot of it is even unconscious. So there are nice evidence that the way the robot moves in terms of speed can change the velocity with which you move, or again the fact that it is passing you an object with a certain behavior immediately change the way you will manipulate that object in terms of rigidity, weight, and effort. And also, if it seems to commit more effort in doing something, you implicitly will commit more effort in doing for a matter of reciprocity. So those kind of implicit, they should not be associated with a change. Different story is about the suggestion or the proposals. We haven't directly tested your question, so whether the change in opinion is associated to a change in physiological responses, but we did a study in which the person was facing proposal by an agent on the scene or by the robot in a sort of video game setting, but with the idea of playing along social engineering threats. And there we actually found out that the physiological response, like electrodermal activity, pupil dilation, again, they react to that. And they can also actually be used by us to understand whether the person has recognized the threat and even with a short time predict a bit whether the person is going to fall or not for the threat. But your point is interesting indeed.
Okay, thank you. So, from the audience, thanks. There is the microphone from our guys.
Thanks, Alessandra, for the very nice cognitive collaboration aspect. I have a simple technical question on the low level side. So when you show the motion that I mean, related to the fragility or not of the object, so these robot motion are learned from I mean the experience of the human, so collecting data by demonstration, or you choose class of trajectories, let's say bang bang or polynomial, and then you scale it. So you have a mathematical model of that motion with parameters, or you're just data driven. Okay.
Okay, in the fragile condition, we actually went for the data-driven approach because we found out that it was effective and starting from we couldn't find the best way model driven to really capture this modulation, whereas for a previous study in which we worked with weight, so expressing the amount of force that is necessary for lifting, then we went for a model based approach and that worked. So it worked, of course, in certain conditions in the settings that we are testing. So usually we try to combine both approaches. So and I'm thinking that also for what pertains the execution of the style, so instead the aggressive versus kind, at the beginning we started with a very simplistic model-based approach where we are assuming that aggressive meant just faster, practically. So classic biological inspired velocity profile, changing the peak speed. We tested it. And even if a person, if asked, could recognize the two, when it came to neurophysiology, the brain didn't recognize them. So we had to move to retargeting because this captured something that we didn't think was important, which is instead apparently quite crucial. And we're still trying to identify how to properly model that. Thank you.
Yeah, thank you, Alessandra. Um, I, I'm intrigued by the always-on robot. I remember COG in the old times at MIT also tried for some time, didn't succeed. But today we have ChatGPT that tells you things about that you discussed a month before. What are the challenges today? Where are you in that regard? What are the difficult things to do? it's just big memory that you need, or you have to forget something? How do you decide?
Yeah, no, you touched a point, one of the biggest challenge. So for us, it's not the problem of memorizing, but it's the problem of forgetting, or better, recall is really the thing. Because we don't want a robot to remember everything. Um, exactly for this cognitive compatibility principle, we would love a robot that somehow has similar ways of us to remember things. So, one big challenge is understanding for us what is the minimum ingredients that you need in this cognitive architecture to allow that. And we have not come yet to the final decision, but we think that endowing robots with drives or goals could be an important step, because in humans, we know that both our affective state and our intention color the memory and determine what we remember, what we forget, and the priority of the things we recall. So we believe that a good way of modeling that could be favoring the possibility of our robot to recalling. So I think that this is the first big challenge. The other big challenge is what to group, what to connect. Again, in a sense of when I remember something, I have a lot of analogies that are available that are really dependent on my life, on my past experience, are unique to me. And they are also very powerful when it comes to, create or find novel solutions to existing problems. And identifying the way to create such analogies in a, let's say, appropriate manner, to me is one of the deepest challenge. Thank you very much.
Okay, thank you. So sorry, but our time is over. So I think that we can thank Alessandra for this presentation. And we leave the floor to the next event. Thank you.
So, good morning, everyone. I'm Paolo Rocco from Politecnico di Milano, and our second plenary talk will be given by Antonio Bicchi. Please, Antonio, come to stage. So there are basically two ways how to introduce Antonio. The first one takes 2 seconds and says, everybody knows Antonio, let's proceed. Second one takes more or less 1 hour and is to list all the achievements that Antonio got. I'll try to stay halfway and just read only the highlights. So Antonio is a professor in University of Pisa and leads the robotics and laboratory of the robotics lab at the Italian Institute of Technology in Genoa. His research work produced a lot of publications read all over the world and cited and earned him several awards, probably the most prestigious one being the Pioneer Award from the IEEE Robotics and Automation Society. He was the founding editor of the IEEE Robotics and Automation Letters that we all know very well. He was the founder and the past president of this institute, the Italian Institute of Robotics and Intelligent Machine, and currently is the editor-in-chief of the International Journal of Robotics Research. But I think that Antonio also is the mentor of many people that are in this room, is a friend and a source of constant inspiration for all of us. So thank you, Antonio, for accepting to giving this talk, and we look forward to listening to you.
Thank you very much, Paolo. Um, yeah, 2 words about this meeting here. I'm so glad that the meeting is going well, lively, happily. The community is thriving, and I did very nothing this year. So this is excellent results. Um, yeah, in terms of the success of our community, which is something that I just want to mention. I just received this. I'm very proud. You know, this is Alessandro gave it to me now. So this is the work of 4 colleagues, Bruno, Luigi Villani, Giuseppe Oriolo, and Alessandro De Luca. And I think this is I didn't read it yet, of course. I just got it in my hands, but I'm sure it will be a reference worldwide. And this is something that for our community, we must be proud of this. So let's get to the talk. And yeah, I think I will today. I decided I will go quickly through some of the past and see where I think we will go in the future. It will not be a super deep talk, I think, but rather touching on things, and I hope it's going to be interesting. So let me start from the background. You all remember, perhaps some of you were not even born, but that was robotics in the 70s, 80s when we were kids. Robots are big machines segregated behind fences, um, humans far away. And then at some point, something changed. And there were a couple of projects. I remember two, but there are probably more in the early 2000. Uh, one was SME Robot, one was Friends, that looked into other problems. And specifically, Friends was physical human robot interaction, dependability, and safety. Those were European projects funded by the EU. At that time, we could have collaboration with industries. You see that we had KUKA in there. Other partners were Rome, Alessandro De Luca, and Naples, Bruno Siciliano, and DLR. And last, it was possible to look a little bit beyond the 3 years long length or 4 years length of the project. And I know that I'm preaching the wrong crowd. I know you are all in favor of that, but today the perspective, the horizon is too short. I think we should say that Horizon Europe, if this is the horizon of Europe, this is too short. We have to look for it. And the reason is that while we did these projects, we started looking into things that were not there simply, like assessing the damage, the real risk of having robots close to humans that forced us to keep those fences around the robots. And in this project, we did the first tests and we assessed those results. Now, how do things work from university research to the future? So these results went after a little while into standards. And that was crucial to enable the use of robots, collaborative robots, in industries. If you do not have standards, you will have no insurance paying for any accident, so you don't deploy the robot. Once you have the standards, then you could have rules and you could deploy. And that led to the birth of a whole sector of robotics, which was collaborative robotics, that is around 10% today and growing. And these are a few of the collaborative robotics that, to me, marked the first and second decade of the 2000s. And question is, what is going to be next? And I believe that AI is definitely going to be important, and it will be AI fleshed out in our bodies. So you have seen these. This is from the early part of this year. This presentation, everybody, we are witnessing, we are with awe what AI is generating. But we all agree that next challenge for AI will be physical AI, which is robotics. This is Jensen Huang at the CES opening in January. So 2030, I think, will be the years of human-centered technology, and and robots that for the people, robots that are useful and usable by the people. You know that you know that my main domain, let's say my passion is for hands and the way hands connect to the intelligence. Another project that I wanted to remind with few friends that are around still are was the hand embodied. That was a project where we collaborated with others, including Siena in Italy. And in this project, we started from the observation of how the complexity of the hand results simple to the brain and to the users. And again, the main result of THE was uh, theoretical in some sense, was this architecture that proposed the organization of the multiplicity, the massively abundant uh, motor and sensor uh, level of our manipulation into these funnels that are synergies that go to the upper level and are closed both through a cognitive high level path, but also through what we called at that time early sensory motor synergies that we now tend to call uh, sensory motor contingencies. Um, Following uh, that intuition, we started developing the hand, the soft hand that you probably know. I will not give too much details about that. So this is the hand at work. It is a very simple hand that still can do things. So in robotics, the hand had some success. It's been used since more than 10 years now. And here are a few results of these. It is interesting that some of these features of the hand are still not achievable by automatic programming. Some of these are hard coded, and some of these are teleoperated. So in this case, uh, programming and AI, if you want, is still a bit lagging behind what we can really do with the hand. But the next step, important to us, was once we had a decently working hand, was to think of prosthetics. And here starts a voyage that was very interesting to me. So this voyage into prosthetics and human-centered or technology or human integration, as I will call it in a minute, we started again 10 years ago, I think. And this was transformative for my research. So prosthetics means doing artificial hands that are robots, basically, that are connected to a person, physically connected and cognitively connected. Key problem is that our nerves connect the cortex and the central nervous system to the hand through some 350,000 nerve fibers. Uh, and that is daunting. How can we control that? How can we imagine to substitute that? And again, that is the contribution that the study of synergies have somehow helped to do. But that was not the only problem that we were faced. So these are some of the artificial hands that are out for prosthetics, the commercial one, the most well-known ones, that have different degrees of different degrees of complexity, different degrees of anthropomorphism. On the left, you see the most simple, just cosmetic, and then you have the hook type, which is very functional, very hard to beat. It's like PID. It's very difficult to do better than PID. It's very difficult to do better than the hook in prosthetics. And the and on the right you have the more advanced models. None of these must be said are clear winners. Some patients that we've met and we've learned from had one of the hands on the right, but didn't use it in favor of the hook. So it's not just a matter of the cost of these devices, of this technology. Some of the hands on the right cost maybe 40, 50,000. It's not just affordability. It's just that they're abandoned, even though they are available, they are abandoned because of the cognitive cost of using a complex device like that. If you have a hand that has 4 or 5 degrees of freedom, like those on the right, you would need 4 or 5 inputs from the person to drive the hand. How can you convey that? Basically, your inputs in reality are just, most the cases are EMGs, and you can only control voluntarily 1, 2, maybe 4 muscles. But 4 muscles is already very difficult. So typically you only use an agonist and antagonist pair, and you control 1 degree of freedom, open, close, for instance. So how do you use the more degrees of the hand? Like, how do you switch from pinch to power or to other operations? You have to send signals. So one feature is, for instance, you co-contract 2 times and you switch in a series, in a ladder structure. You know that if you switch twice for 3 times, you will go from pinch to lateral pinch. And at the end of the day, the time and accurate and attention that it needs to count every switch is too demanding. So people abandon often or use very little. So some feedback we had from people, for instance, was I asked one person that had both a Hosmer hook and an advanced hand on the right. We asked them, which one do you use? And they say, well, it depends. When I go out, I show off the high-tech hand. At home, I always use the Hosmer. And so this is a lesson, but this is not the only reason why those prostheses are not enough. Another reason is that we also use our hands for things that are different from manipulation and grasping. We use our hands to touch our own bodies and to touch other people's bodies for social functions. As in this case, if you try to do this with some of the hands that are out, or some of the technology that is out, that is very clumsy. You would never do that. What is the reason? The reason is basically they are stiff and they don't feel like part of your body. Indeed, nature is almost always invariably soft. And softness, together with the synergy idea, were the enablers for our design. So this led us to the design of the Soft Hand Pro, the hand that we use for prosthetics, that has still only one input that suited well for the simplicity of the input that we need from for patients, for subjects, but has the full 19 degrees of freedom mobility of the human hand. So it can conform, it can adapt, it can take shapes that are non-trivial. All 19 degrees take the shape And in this sense, in the sense that you have on the right there, we say that it's really the object that manipulates the hand. The shape of the hand comes from the object interaction, which is something that is, now more obvious than it was at the beginning. And an important thing is that if the hand is soft and natural to use, then also in the social functions. So now we have a robot which is connected to a person that is used for, for doing this. So, and I think that we came some way from this. And this is something that I like to, at this point to remember. Of course, there is a lot beyond that. I also only spoke so far about the actuation part, the motor synergy that I showed before, how to reduce the number of inputs that control many degrees of freedom. But there is the necessity for addressing the other part. So in this project, we wanted to really try to build something that was, comparable with feeling the hand as part of your body. So this is the ideal of perfect human robot integration. You use something as if it was your body. What would you need? Of course, we will never get there. But what would you need to do that? And in this project with Dario Farina and the surgeon Oscar Assmann, we started investigating what is needed for closing the loop. So in this project, we the surgeon did surgery on the nerves that used to innervate the hand, so that now they move muscles in the stump and also receive inputs from the skin on the stump, on the residual limb, I should say. And by Dario Farina's algorithms, it can talk and define and describe the motor neurons language, the spiking motor neuron language that comes from the spine. So what is our role as a roboticists in such a project? Our role was to connect this biohub, this input-output port that is created by the surgeon and the neuro scientist to the robotic part, so that we can send signals and receive from the hand signals, but not just any way, in a specific way, in the specific way that we expect it to be generated. And here I'm very glad that Alessandra did that beautiful talk before, because she introduced this idea of prediction, expected output, which is at the core. I refer to this paper. I don't know if it's the earliest one. Alessandra, you're even more, you're for sure more expert than me. It's Johansson and Edin that have this very nice paper on predictive feed-forward sensory control during grasping and manipulation. They are not control engineers. They're not roboticists. They're neurophysiologists. But I have this beautiful paper on the fact that it cannot be just feedback that drives manipulation or action. It has to be also feed-forward. And the feed-forward works in this way. Every motion plan that we do with our hands, but with our bodies more generally, is made of two parts. One is the motor action, and one is the expected sensory output. So it is more like the brain prepares a packet to send to the periphery that has both the sequence of motor movements and the expected pattern of the result. And how do we match that? Because we have learned through interaction with environment, we have learned what will happen if I do that motion pattern in the environment that I see. These are called sensory motor contingencies, things that happen together in the sensory and motor domain. So in robotics, we have to build for this ideal natural bionic system to have to build something that will generate through a motor action something that is close to the sensory expected for the natural body, which is not at all trivial. But at least we have a direction where we would like to go, a theory, let's say. So if you consider that this is important, then another conundrum is that if you look at, I said 350,000 fibers, but they are not equally distributed between afferent and efferent. Surprisingly, at least to me, there are only 30,000, sorry, to 50,000 nerve fibers that are efferent, motor actions, and 300,000 that are afferent. So the sensory part is devoted the largest part of the inputs that we receive, of the communication with the hand from the spine. This means that just doing the motor part is not enough. Clearly, I mean this goes even farther. I mean, when I saw this result, I was surprised. The author of this work says that motor control is actually a sensory phenomenon by 9 to 1 basically, or 10 to 1. Here is Oscar Assmann, that is the person having done the study, replicating a famous study by Edin and Johansson, and injecting an anesthetic in the radial nerve of Alessia Ivani and Eleonora Fontana, who are not here, but are students in our group, that then, deprived of the tactile sensing of the fingertips, are become very clumsy and unable to do manipulation, just to underscore the importance. So it is important that we bring back information from the hand, but again, on one side, we have to focus the information in few manageable channels, and on the other hand, it's not trivial, it's not easy. So there is work that we have been doing with Federica Barontini, Alessia Ivani, Eleonora Fontana, and we are still doing to bring this sensation back. And it is important, but I have no time to go into the detail. So final part is next, what we are doing today, what we've learned from doing prosthetics and how we apply more generally. So yeah, from prosthesis to person extensions. Prosthesis can be at any level. You can imagine the hand going up and up, or you can use exoskeletons, or you can even imagine having a person that instead of staying in the exoskeleton gets out and uses the exoskeleton as an avatar. Why not consider that as a prosthesis? It's a whole body prosthesis, if you want. That's the only point that we have. And this is what we call human-robot integration. Still, we would like to have the same result of perfect, seamless human-robot integration. So the avatar body should be felt and seen and lived as if it were your own body, or an extension of your body, if you want. Of course, it has a lot to do with teleoperation. Now, teleoperation has been around forever. Sometimes in robotics, we tend to disregard teleoperation, like, oh yeah, but that's just teleoperation. Yeah, but teleoperation is something that has produced the best results of robotics so far, by far. Teleoperation started in Italy in 1959 with the mascot. But then this is in real because there were others in the Argonne National Labs. But the first real success story that is still working today in Colham in Oxford is this one. And of course, Da Vinci is teleoperated. And all the drones that are around are mostly teleoperated now. Of course, autonomous technologies are surfacing now that, unfortunately, the robots are used for applications where we wouldn't like to see them and to combat jamming. So in teleoperation, let's consider teleoperation for a second. Of course, we have the central nervous system, our body that controls some interface that controls a robot that interacts with the environment. Much of the attention of research has been devoted to managing the trade-off between transparency and stability because of the delays that happen in communication. This problem is, I think, well understood now. We know exactly for a given bandwidth how much you can have in terms of transparency for preserving stability. There is another aspect that has not been considered as deeply, which is the fact that when you interact between the teleoperated robot and the environment, and you bring back sensations, you would like to have a consistent sensory motor synergy. You would like to feel something that is meaningful or similar to what you have. So it's basically the same idea at play that we had before. To have a similar interaction with the environment, for instance, you would like to have a soft body because our bodies are soft. So we learned interaction of soft body with a soft environment. You would like to have accurate haptic feedback. And then we started to do some exoskeletons, some avatars. First one was use of Walkman in the Amatrice earthquake in 2016. Then we've done some experience with the Ocean One robot of Stanford by doing exploration in the underwater. It was a beautiful cruise in search of the wreck of a Roman vessel. And more recently, we started exploring with the use of alter ego, other dimensions. Alter ego is this little robot that has autonomous capabilities. It can be among people. It can walk, take your hand, follow you, look at you, do all the nice things that now we are used to see in robots. Can also do applications like guide in the Adrian Temple, if you want. I think it's still operative. It's been operational in the Adrian's Temple downtown in the city, where you can go and see it doing the introduction, navigation, and so on and so forth. And it has been used in RAISE, for instance, for the aquarium in Genova or other places. And we are collaborating with Alessandra on these aspects. Yeah, this is the navigation. But what I think is more interesting to me is the use as an avatar. Not more interesting to me, more interesting today in the line of this talk, looking at it as an autonomous robot who accepts human inhabitants. It has soft muscles, soft hands, tactile, visual, audio feedback, and tele-impedance control, which is something that was developed with Arasha Judani some years ago. We only use wearable interface. We do not use force reflecting exoskeletons, both for simplicity and for avoiding the stability issues. And through these devices, the person can see, of course, through the eyes of the robot. The robot moves the head. You feel what the robot touches, moves the hands like you do. And come on, yeah. And we have tactile sensing so that you can explore surfaces in a completely different room or even different city. And you have a return of these vibrations. These are high fidelity vibration rendering that we found works very well in terms of conveying important information. And for simplicity, it is implemented in the um, remotes. Uh, and it has, of course, some degree of supervised autonomy. So, for instance, for doing tasks like opening a door, it would be impossible to do that in teleoperation alone. So the robot introduces stabilization mechanism, look for the position of the handle. In this case, there is no handle, but there is a slider for completing tasks that would be difficult. And the final thing is we want to put human-like robots inside average homes for doing things like, sorry, like tending to your pets while you are in travel, opening the door to the bellman, um, or to the postman, or attending some people that might be in the bed. So, final to close with, the what is the experience of using a robot that has characteristics that tend to replicate your sensory motor contingencies? Experience that I can tell, but also some colleagues have tried, is that after a little while that you see the world with these eyes, and more importantly, after a little while that you are acting on the environment, because the agency on the environment is very strong in convincing you that you are really there. So you can go in this direction, you can open the door, turn the handle, go another room, explore, talk to people, do things, take a coffee, come back, go for. After a little while that you are doing that, you come back to the room. And if you see yourself, your own body, you typically jump up. And I did myself. Because you have forgotten that you have another body. And it's surprising. So there is an expression in philosophy that is a famous book that is, what is it like to be a bat? Can you imagine being a bat? And the discussion is, well, it's very difficult to do this experiment. It's a thought experiment because, yeah, you can imagine what it would be a bat with your human brain, but what about the bat? So I think we in robotics we have the ability to do something more measurable, which is what is it like to be a bot? After a little while, you are a bot. What can you do? How do you change your ways? And one interesting thing that we are doing is we are giving our robots to artists. Unfortunately, I have no artistic talent myself. I love art, but I cannot do good art. So I do halfway. We let robots uh, do art through artists. So the artists can become robots. And for instance, here is part from a theater piece that was written and played by Dario Focardi that has been played in Italy for several reprisals. Here is the author, and there is another actor outside, and they interact on stage. Now, of course, there is a need for some technical, you know, you have to put that on stage, and it has to work for 1 hour act. So it was not completely trivial, but it was interesting, and the experience of the person of the actor was interesting. And another one was this painter Melchior in Genova, who not only designed the cover of the robot, but also maybe I don't know if I have audio. Uh, e questi sono gli autoritratti di Melchior attraverso il corpo di Aperego. E con questo, ma non prima di aver ringraziato il gruppo che è fatto di tantissime persone, in particolare Manuel Catalano, Giorgio Grioli, ma tutti gli altri che vedete qui sono stati importantissimi, Francesca Negrello e tutti i ragazzi anche di Bergamo, di Genova e di Pisa. Vi ringrazio per l'attenzione.
So thanks a lot, Antonio, for this incredible journey into robotics. So we are a little bit behind schedule, but I asked the organizer if we can reserve space for at least a couple of questions. So anyone? So I'll start off maybe. So when we founded this institute, together with other colleagues, also with Alessandro, the motto was Diamo corpo all'intelligenza artificiale. So let's embody artificial intelligence. So after 6 or 7 years, I can't remember exactly, what is your opinion? Where are we now? Particularly in all the devices that you show, like the hands, the prosthesis, the exoskeleton. Are we actually embodying artificial intelligence in all these things?
Yes.
Good.
I think so. I think so. Not in the specific technology of hands or motors or other things. I think we are seeing these more and more. For instance, the supervised autonomy that we are using in avatars, that is using some of the tools of AI. I don't think that embodying that fleshing out AI is just the matter of using a neural net for doing visual recognition, though. Of course, that is the way to go. I mean, if you need to do visual recognition of objects, no way you will escape from neural networks today, right? So that is for sure. Um, so indeed, in thinking of what the meaning of expanding AI or extending or embodying AI is, I think, well, my take is that I'm interested in this direction of human robot integration that is more interesting to me than pure AI, even through a robot body, or of course classical robotics. So think of heart that I mentioned in the end. Uh, yeah, you can do paintings with a robot that has a, driven by Dali and will do something. Who cares, right? Who cares? As a piece of art, yeah, it can do that. I don't care. Can be graphic, maybe can be useful for making slides, but it's not art. So I'm more interested in this, human robot connection to have the human involved into that. That to me is
So first of
Emanuele
all,
Menegatti. So
thanks a lot for the beautiful talk. I'm interested in this concept of interfacing to the body of the user or the human. Uh, you showed different interfaces. What do you think is the more promising, at least in the application you showed? So is the interface to the nerves, to the muscles, to the spine, to the brain? Which is the level that, in your opinion, is more effective?
You mean for
Yeah, mainly
prosthetics?
for prosthetics. Yeah,
Prosthetics.
yeah.
Well, I can tell you my point of view. Interfaces through the nerves, invasive nerve electrodes, seem to me to have reached the point where they showed some results, very interesting results. I don't see that going much forward just because of the complexity. You can put one or few electrodes in a nerve that has hundreds of thousands of fibers. So the specificity is going to be very little. So there is some feeling that you can bring back, but not very detailed. So that is, I think, a limit of the methodology that will reach a plateau, and I don't see it going much further. But maybe I'm just wrong, and a new technology will come. If Neuralink works, then who knows? The other methods that you said are more non-invasive. I'm more interested in non-invasive methods. Among these, what is the most important to do, for instance, for haptic feedback? That's a great question. It would be beautiful if we could have the synergies of feedback. In this sense, the drawing that I made, if I could take the PCA of all the 300 afferent signals that come through my nerves, and then say, okay, this is the first synergy. This explains 80% of the, or 50% of the variance. That as a thought experiment would be great, because that would be, the thing that you want to measure first and reproduce first. It's, let's say it's not trivial as an experiment. But that is the idea. Calogero.
So yes, we have time for maybe one quick question and a
Yeah,
quick answer. Yes.
yes, very quickly. Thank you, Antonio. First of all, uh, we have seen a lot of progresses. However, robots are still not around us. If you have to say one or just a few needs and enablers that will trigger the robots to be here, uh, what you will bet on?
Well, first of all, don't discount the disappearing robot paradox. When a robot will be here, you will not see it. You will not call it a robot anymore. And we are seeing many robots, not just the Roombas, but unfortunately many DJIs, or many quadruptors are around. The war that we are unfortunately seeing is a robot war today, and we have to to recognize. So when the application pool is strong, robotics is coming. It's sad, but it's true. And to see it at home, I think partially is a technology. We need some more technology push, but I think it's more an application pool that is missing. Once we really want them at home, or find the killer application, then they will come. Because today, technologically, we are close. We are much closer than I thought. The future of robotics is perhaps that industries will come and take it over, and it will be more difficult for us to do research. Robots are becoming more and more commoditized. How do they say? The number of humanoids that are being produced, the technology for building robots is progressing a lot. there is little understanding of the use of robots. How can you use a robot so that is easy to use? The key question is, can my mother, uncle, use a robot? Of course, we can use it, but as far as we only can use a robot, they will not come into operation. Our friends in humanity, our friends in uneducated friends, when they will be able to use a robot, then robots will come, I think. So it's interfaces, and this kind of work, I think, goes in that direction.
Okay, so I think that in the afternoon we will have a session dedicated to whether we have to use humanoids or not. So that fits extremely well with this discussion. So let's thank again Antonio. And then I think that, I don't know, Elena will give announcement on what will follow.
Yes, so now we have the coffee break. Please be back at 11:15. We have the assembly and RoboIT presentation for funding in robotics. So 20 minutes coffee break now.